Good morning again, folks. Just a quick heads up, I am recording in a different room than I normally do, so the lighting might be a little bit off. Hopefully this is the only time I have to do it. My husband got pulled into a pretty much all-day conference, so he's taking the office today. Um, so we are going to move into a new section of chapter 9. You're going to notice my pacing. If you kind of looked at the textbook for chapter 9 and my pacing for chapter 9, we are going to kind of bounce all over the place in terms of the sections. But I promise you, it's for my own teaching sake. I think it makes the most sense to kind of do it in this order. So then at the very end, we can kind of cluster a lot of skills together and make a really good connection of all the concepts chapter wide. So we are covering a very important formula today. It's called the law of sines. And for the rest of the chapter, essentially, we're going to be focusing on what's known as oblique triangles, which are triangles that don't have a right angle in it. So we're going to be dealing with some formulas and areas that aren't the standard from geometry. So what we have is in an oblique triangle, we have angle ABC and then side lengths ABC, which are always going to be opposite their respective angle. So if I mention a side length B, it's always going to be opposite B. Side length A is opposite A. And secondly, for my own notation's sake and for the book, they always use capital letters as angles and lowercase letters as side lengths. So that's just a standard notation. So back to the formula. So the law of sines actually is a really powerful but very simple formula, and it's actually a ratio. It's a series of proportions, really. If I take sine of any of the angles in a triangle and divide it by the opposite side length, that proportion holds congruent for all three possible proportions. So sine A over side A, sine B over side B, sine C over side C is true. And of course, if I reciprocate all three fractions, it doesn't really matter which of these you use, they're equivalent. So let's just kind of jump into one example today, and we're only going to work with one example. This is, and I can probably guess some of you are cringing whenever I see these three letters together. We're going to solve this triangle, and the information that's given to us is an angle side angle triangle. So two angles and the included side, meaning the side in between the two angles that were given to us. And we're going to be asked to solve the triangle ABC, meaning find all missing information. So first off, I'm going to just label that we need side A and side B, and of course, angle C. So we have three unknowns here. One of them is probably the fastest found. I mean, if we have two angles of a triangle, we can subtract and get the third one pretty quickly. We know all three angles add up to 180. So a 110 plus 20 is 130. Take that away from 180 and you get 50 degrees. So one of those is pretty straightforward. Now this is where we're going to actually use my formula. And I'm going to use the second version of it because usually if I'm solving for a side length, I like those to be in the numerator position. So for example, we now have a complete pair of opposites. So angle C and, sorry, angle C and side C are given to us. So if I go 25 over sine 50, and I set that equal to, let's solve for side A first, A over sine 110, I now have an equation with only one unknown that I can solve. So now A equals 25 times sine 110 degrees over sine 50 degrees. Now keep in mind these are degrees, so make sure your calculator is set in the appropriate mode. And of course, this is an open calculator chapter, not that I could stop you anyway from my basement, but making sure you're in the right mode, A, and we're going to around this quite a bit. I'm getting about 30.7 meters. So 30.7 meters would be side A. Now we can set up another ratio very similar to find side B. I'm going to stick with the given information, the exact information, rather than using this ratio here because it's rounded already. And if I use that to solve for a secondary piece of information, it's even less accurate than the first round of rounding. So I'm going to stick with 25 over sine 50 again, because those are both exact. And I'm going to now find b by dividing it by sine of b, which is 20 degrees, excuse me. So now we know b is 25 times sine of 20 over sine 50. And again, this becomes a calculator problem, and it's going to be rounding again to about 11.2 meters. So we have 11.2 and 30.7. Now, there's very little you can do to absolutely check all of these, but there is a little reasoning you can apply to your answer. A is the largest angle. It should definitively be opposite the largest side length, and we see that. B is the smallest angle, and it should be opposite the smallest side length. And again, we see that. And of course, the middle size angle and the middle length side should always be paired up as well. Okay? For the record, we're going to spend another day on this because it does get more complicated than this. You should probably know better than to expect something as simple as a quick ratio, but we will discuss that in tomorrow's lesson. So get started on the section 9.3 homework, but by no means do I expect it finished by tomorrow's lesson.